Okay, so let's go through one more example here. This one we've got a pinned connection on the left here. We've got a roller connection kind of in the middle here and a bit of an overhang here with a distributed load on it. So just first off, recreate the diagram. Need to convert that into a free body diagram. So again, we remove the supports and replace them with the equivalent forces. So I got an x at A and just y's at A, and at just y component reactions at D, and obviously also a y connection at D. So we're working in the xy plane here. So first off, let's just get rid of that AX. That's equal to 0 because the only thing force acting in the x direction. Next thing we're going to do, we're going to take the moment about A. So moment about to that point. So got the 20 kips. Again, that's going to be a negative moment. This 12 kips here at 14 feet, that's going to be a negative moment. This reaction here at D, that's going to be a positive moment, assuming the direction is correct, which it is. And the moment caused by the resultant of this distributed load. So that distributed load is 1.5 kips per foot over an 8-foot span, gives us a resultant of 12 kips, and it is acting at a point that is kind of right in the middle of that 8-foot overhanging span there, so an additional 4 feet past the support, so 28 feet. And then based upon that, we just got the one variable left, so we're able to solve for dy. It's 26 kips. Then we can go and find out what our AY is just by taking the sum of the forces in the y direction. So AY minus 20 minus 20 minus 12 plus 26 minus 12 is equal to 0. That gives us 18. So what I'm going to do here is just redraw the free body diagram with the amounts listed. 18 minus 20 minus 12, 26. And then again, since we're trying to recreate we're trying to make what the shear force actually does in there, so we're going to keep the distributed load. We're not going to have the resultant in there. So just systematically, we're going to work from left to right. So 18 kips pushing upwards on the beam means that from the start, we move up 18. So we're moving up here. Then it's constant for this span until we hit this 20 kip one. So that pushes us downwards because it's pushing down on the beam. So there will be at minus 2. Minus 2. It's constant there until we get to this 12 kip load. And then we are going to be at minus 14 for this span here. Then we move over here until we hit this reaction here. So that adds 26. So minus 14 plus 26, that gives us a 12 kip load here. And then we have the distributed load that is pushing us downward. So it drops off us off at 1.5 kips per foot. So again, 12 feet times 12 kips minus 1.5 kips times 8 feet brings us all the way back down to 0, which is exactly where we expect it to be. So there's our shear diagram. And then we can create our bending moment diagram. So again, got a pinned connection here, so that's going to be 0, and we got a free end at the other end. That's going to be 0. Please note that we do not necessarily have zero bending moment at this pin connection here because it's in the middle of the load and there's still forces on either side of it. It's only when we have the pinned connection at the end of the beam that we necessarily know that the moment there is zero. So we can start from the 0 point. We know that it's going to be increasing because the shear here is positive, and it's going to be increasing at a rate of 18 kips per foot. 18 kip feet per foot. So that is a 12. That's a 6 foot span there. So 18 times 6 gives us 108. So we increase all the way up to here. And then the shear drops down because of that point load, and it drops down to -2. So now we know that the slope in this section is -2. -2 kip feet per foot, basically, is kind of how it works out too. So the feet kind of cancel out. So the value of the slope is just your shear load, -2 kips. So working from our 108, we take that and then we subtract 2 times the span here. So 2 times 8, 108 minus 16 gives us 92 kip feet. So that's the value here. And then we get to this other load here. And then after that point, our shear decreases further. So it's still decreasing, but the slope's a lot higher. So start shooting down and keep shooting down until we hit this support here. So the value that it is going to be decreasing is going to be -14 feet times that 10 foot span, so -140. So 92 kip feet minus 140 kip feet is -48 kip feet. So that's the value at this support here. And then after that, we know that we're going to get, after that, the shear shoots up again, so it's positive in here. So over this span, we're going to be increasing. So the amount that we're going to be increasing is just going to be based upon the area of that space there. So again, what's the area there? We got 12 kips is our shear times 8 feet divided by 2. That gives us 48 kip feet, which is exactly the amount we need to get us from here up to here. So the manner in which it does that is going to be the kind of the shape of the line from here to here is going to change, and you need to the shape of the line from here to here is going to change kind of based upon what is going on with the shear. So we know the distance, but it would be a different scenario if the shear, instead of looking like this, if it looked like that in this situation. The total amount of change in the moment would be the same if the area was the same, but basically we need to keep in mind that the slope is proportional to the value of the shear. So at this point here, when we're getting close to the ends, where there's very little shear, the slope is 0 at the very end and small, and then it starts to increase, and then starts to increase until it hits its maximum. And so, yeah, Whereas if we had a shape that looked more like this, it would be starting off as 0, going from left to right, and then doing that. So same distance, same vertical distance on the moment diagram, but a different way of getting there. So just keep that in mind. So always keep in mind that the slope of your moment diagram is equal to the value of your shear diagram, and that'll let you kind of fill in the gaps of when your moment diagram is changing the fastest and when it's changing the least.